soon as the recording starts. Okay. Welcome back to second week of yes. Archie.
Bir de yabancı dersler var, bilgisayar dersleri falan.
Thought I accepted all the requests that came in at the last minute.
Yağmur mu?
The last request was Celine.
İnşallah. Onun yanında başka üçüncü sınıfta başka dillere
Everyone who so far has requested to join the team is now a part of the team, I believe. Okay. All right. A couple of things. One, I've set my quote unquote office hours. So what I will do is I will be available. My plan is to actually be physically on campus for those of you who are in Antalya and would like to meet face to face. My plan is to be on campus during these hours, but it's going to be 9 o'clock to 11 o'clock on Wednesdays. For those of you who are physically unable to come to Antalya or to the university, that's fine. Just basically, my plan will also be to have my Microsoft Teams up, or if there's some other type of way that you would like to talk to communicate, then we can set that up as well. But I'm not scheduling anything else. There's not going to be anything else I'm going to be working on during 9 to 11 that I won't take myself away from in order to spend time with you if you need that. Okay, I know, I think the first year class, I think you have a class during that time. So I'm sorry I wasn't able to set it at a time that was more convenient for you, but you guys are actually kind of quite full schedule-wise, aren't you? So, anyway, so I wanted to put that out there. The other thing I wanted to say that I'm gonna experiment with. So I've been trying to figure out how to do attendance and quiz and stuff like that. I think one of the things I'm going to do, so what I've done, I've put kind of an easy one in for this lecture, but what I'm going to do is some of the slides, so what you have access to through the Microsoft Teams SharePoint folder, what you have access to is the slides as they should be, okay? And the reason why I say it that way is what I'm going to do is I'm going to take some of them, I'm going to edit them but not save them to add like fill in the blanks, maybe you know, other types of things that are not quite right that I want you to notice, and I want you to say, oh, hey, wait, there's a blank there where there should be text. There's a blank there where there should be information. And so what I want you to do is when you see that is I want you to write into the chat for this class. I want you to write what should be in the blank. So for this lecture, at some point we're going to hit a slide that's got some blanks on it where there should be information. I want you to fill it in. Now you don't have to fill it in with what's on the version of the slide that you have. You can fill it in with the stuff that I say. Okay, so maybe I'm going to expound on it. I'm going to say what these things are, and you can fill it in. I hope that's clear. So, I want to make sure you're paying attention because, again, for me, it's not just about joining the call. It's not just about sitting at the computer and watching the screen. It's about being able to be interactive, about answering questions and asking questions and making comments and discussing these topics. Okay. All right. Actually, I just got a couple more requests in at the last minute, so let me go add these students to the class, and then we can continue on. Okay. All right. So even on Microsoft Teams, we have some late joiners to the class, I guess. All right. So let's get going. So let me go ahead and share my PowerPoint here. Okay. See, again, what you should be seeing right now is my PowerPoint window. Okay. This is where we left off. I'm gonna go back to where we left off, but first I want to do something that so those of you who've had my classes before know that I like to do this. is I like to start every class off with a quote of the day. So this is going to be some quote from some person either in the computer science or engineering field or some scientific or technical field, most likely, okay? Or it's about computer science. It could be, I think I have a really nice quote that I like from Queen Elizabeth of England. All right, hold on, let me close the door. I think the sound is probably... Okay, so Edgar Dijkstra tells us that computer science is no more about computers than astronomy is about telescopes. What does that mean? A lot of times we think that computer science is all about making computers. The truth is that computer science, computer engineering is actually about solving problems. It just so happens that tool is the computer. So just like astronomers, astronomers don't study telescopes. Astronomers use telescopes to study the stars. And in the same way, computer engineers, computer scientists, we are not as concerned, some of us are, about developing computers, computer components and electronics, but really what we are about is solving problems. Okay, and we happen to use computers to do it. So let's talk about how we solve problems. So where we left off, we talked about algorithmically to do scientifically and algorithmically to develop a solution to a problem, right? So how do we do that? Well, we start with the overall goal. We have the idea of what we want to do, and then what we need to do is we need to divide that problem into smaller problems. And then we keep doing that until we reach some activity, some problem that is easily performed, that is easily solved. And then we put the solutions, the small solutions, back together into some overall solution. So, if the problem is we want to build an airplane, we don't just start with build an airplane. We don't just go out and do it. What we say is, okay, well, what do we need? Well, we need an engine, okay. We need wings, okay. We need the body of the airplane, and these kinds of things. And we divide the problem of build an airplane into smaller and smaller goals, and we develop solutions to those small goals and put them all together, and we get an airplane at the end. In the same way, as an example we'll look at here is learning. And if we were running this PowerPoint like as a show, you would see this nice little animation that would happen where we'd start out with the word learn, and then we would come out into all these other things over here, right? So learning is a task. It's something we want to do, but learning isn't just something we do as a simple task. There's a lot of parts to it, right? We need to prepare, study, and reinforce, for example. And how do we prepare? Well, before we come to class, we read and we make notes and we maybe prepare questions for what we want to ask. Well, what do we read? So even reading is not a simple task on its own. I can read, right? I can read anything. I could read everything. If I were to tell you read everything there is to know about writing Java programs, it would take you a long time to do that, right? So what do we read? Well, we read lecture notes. We read maybe the textbook if we have it. How do we study? Study is comprised of different tasks as well. All right. Or we attend the lecture, we listen, we complete practical exercises, right? Stuff like that. All right, and reinforce after we've learned something, after we've prepared and studied something, we reinforce it. So we do it again. Okay. So let's talk a little bit about tools that we have available to us in order to write these algorithms, to design these solutions. Because many of you, what you're going to do, if you are like me, if you are like I was when I was a first year programming student, yeah, what you'll do is I'll give you an assignment to do. You'll go sit in front of a computer and you'll start typing code. Right? You'll start typing Java code because you think that's the best way to do it. The truth is that what would save you and me a lot of time is if you made a plan on how you wanted to solve the problem first. Okay, not just the code out, but actually plan out, okay, how am I going to solve this? What type of code am I going to write? What type of, when we get into it, methods and stuff like that. Control structures like if-else statements and loops. What are those? What kinds of things am I going to need for that? Okay, so we make a plan, and then we take that plan and put it into some representation, and we'll show you two versions of that. Some representation that then can be used to write code from that. Okay? And I'm not going to get too much into all this. I do want you to know what pseudocode and flowcharts are. Those are the two important things we're going to go over. I do want you to know what those two things are, but a lot of what I'm describing is part of a larger thing called software engineering. It's this how code is developed and developing a software process of how the process of code is developed. Okay. So what we're going to do is we won't spend a lot of time on this, but I do want you to know about pseudocode and flowcharts. Okay. So pseudocode, the word pseudo, it means like fake or false. If you've ever heard of what's called a pseudonym, it's when some author writes and uses a name that's not really their own real name. So if you've ever heard of an American author named Mark Twain, his actual name, his legal name was Samuel Clements. For whatever reason, I guess he did not think that he could get books and short stories published named Samuel Clemens, so he named himself. So he wrote under a pseudonym called Mark Twain. Pseudocode, as its name implies, is like a fake code. It's not compilable. It's not executable. It's not code that could run on a computer, but it kind of looks like it. Okay, and so it's like a go-between between writing things in maybe a sentence or a paragraph format versus writing things in a code style. So what we can do is we can take something like this, right? If student's grade is greater than or equal to 90, print A. If student's grade is greater than or equal to 80, print B, and so forth, right? What we can do is then we can take something that looks like this and convert it into Java or C or some other language pretty easily. Okay, so this is one of the tools that we'll use. We can use as a software developers, as computer programmers, we can use pseudocode to use regular language, and that can be English, it can be Turkish, it can be anything. All right, but we use this pseudocode language to be able to have us as humans understand a little bit of the meaning of what's going on, but at the same time, then we can then take this and move it into an actual code language format, like a Java, Python, something like that. Okay, this is another example of pseudocode. I encourage you to look at that. Okay, maybe during the outside of the class. Again, I want to get through this set of lecture slides pretty quickly because we need to get to chapter 2 today, and I would like to also do some examples as well. All right, another tool. So this one is a text-based tool. Pseudocode is a text-based tool that helps us be able to convert from English or some some human language into a programming coding language pretty easily. Okay, the flowcharts are useful if you are a person like me who is a very visual person. I like graphs, I like charts, I like pictures. This is how I can understand things much more easily. Flowcharts will help us do that. Okay. So what we have is we have some symbols. I want you to know these 5 symbols on the left very clearly. These are not as used as much, but these 5 over here, you need to know these. So we have kind of this ovally hot dog shaped, sausage shaped start end. Arrows will flow from one spot to another, from an instruction to another instruction, or from the start to the instructions, something like that. These Rectangles are going to be the instructions. It's going to mean where something happens, where just a variable is assigned or some other type of activity happens. Input output, where we either display stuff to the screen or we get input from a user. And then a conditional, like we talked about briefly, we talked before about if statements. So how to do a conditional, we come in, if something's true, we do one thing, if something's false, we do something else. Okay, and it's all about control flow, about how the flow is controlled. Okay, so here's an example of a flow chart. All right, so what we see is, okay, this is our start. Our lamp doesn't work, and this could be anything. This could be a lamp, it could be a refrigerator, it could be, something doesn't work, right? Well, we check, is it plugged in? And if it's not, if the answer to this is no, this is a conditional, this is a decision. If no, if the lamp's not plugged in, plug it in, see if it works. Okay. Otherwise, is it plugged in? Yes. Okay, move on. Is the bulb burned out? Is the ampoule, the bulb, the light bulb, burned out? If it is, replace the bulb and hopefully we're done. And if it's not, okay, then buy a new lamp is the final solution here. I don't suggest that to be an actual good solution, but you get the idea. If something is false, we do one thing. If it's true, we do something else, and so forth. Okay. Some other examples here: ordering a burger, like a cheeseburger or something from a McDonald's or Burger King, which I don't suggest you eat there. It's not the best quality of food, but it's good for a flowchart idea. Okay. And here's an example of if we want fries. So actually, this line, I think, we took this. I took this from a site, and that's actually this line right here. It should be over here. It should indicate that want fries, yes. Order fries, no. It just continues on. We don't have to go through that in order to get to that. Okay. All right. So that that finishes kind of the intro on what it means to be an engineer. Okay. I won't spend much time on chapter 1 here, but I do want to go over a few things. Okay, one is some of the different parts of a computer. Okay, and these are good for you to go over, for you to understand in your own time. But these are the different parts of the computer. So let's kind of just maybe go left to right here. So we have the storage devices, which would be stuff like the hard disk, the hard drive, a CD. Back in the old days, there was tape, right? So this is places where data is stored. Storage devices are what's called non-volatile memory, because when the power goes out, when it gets, or like a CD, when it gets removed from the device, it does not lose the data. Okay, it's called non-volatile memory because it does not lose information. Memory, but on the other hand, is called, this is RAM, random access memory. This is what's called volatile memory. When the power goes out, this gets lost. Now, Microsoft Word and other types of programs like that form files and documents, a lot of them do this autosave thing now. The autosave goes over into the storage device, into the hard disk. But years ago, when I was in your shoes, when I was your age, we didn't have a lot of these autosave features on our programs. So a lot of stuff, if you didn't save it, it was in memory. If you didn't save your changes and the power went out on the computer, guess what happened? Your whole file just went away. All right. So that's why a lot of times we say save consistently, save frequently. Just keep saving, right? But notice that this memory is closer to the CPU, which means it's faster. The reason why it exists, you might be saying, well, why not just make everything out of non-volatile memory? This is faster, and but it is also more expensive. So, but it's faster, which is why it gets used where it does. It gets used for things that aren't intended to last long. Okay. All right. CPU, that's like the brain of the computer. That's going to be the central processing unit. It is what its job is to control everything. It controls the data flow. It controls the processing of instructions and stuff like that. Okay. Then we have communication devices like a modem or like a Wi-Fi router would be an example of a communication device. Input and output devices. Your primary for the computer you're on right now, I would think, unless you're watching this on a smartphone or something like that, your input devices are going to be your keyboard and your mouse. There will also be like your disk drive and maybe some other things. But there's some input devices and there's output devices. You might have a monitor. I'm assuming you're watching this on a monitor. A printer if you want to send a document to be printed. Okay, so this is an example of what composes a computer. So I went through all of this. Again, I find this stuff very interesting. So for those of you who don't know, my my undergraduate degree, my bachelor's degree was actually in electrical engineering. So I know quite a bit about how the electrical things work in all this. So I find this pretty interesting. Okay, so some of you may know this, that a computer doesn't speak English, right? It doesn't speak Turkish either. It speaks in this binary, right? It speaks in ones and zeros, off and on, true and false. This is the way that a computer understands. This is the language of computers, okay? So even every program that's running right now, even this thing we're doing, right? This online education, internet, Microsoft Teams, all of this stuff is actually represented down in the computer as a series of ones and zeros that just are in the right form, right? They're in the right order, okay? So then the question is, wait a second, Hojam, are you going to ask us to write a bunch of ones and zeros to make a program? And the answer to that is, of course, no, because that would be well beyond the semester we have to do that here. All right, so how do we get the ones and zeros into a CPU, into memory to be able to run on a CPU, right? Well, at some point they developed this thing called assembly language. And assembly, there's different types of assembly language. But assembly language was used as there was an instruction like add, and then this is basically what this would do is add register 1, register 2, and put the sum in register 3. Okay, and when you get into your computer architecture, your what's before that, your digital systems and computer architecture classes, if you get to take those, you'll learn all about what registers are and how all this stuff works, okay? So we won't get into that too much today, but basically assembly language was something that early programmers used to be able to convert what was something somewhat understandable to them into this binary format for the computer to understand, okay? So, but assembly language is even a bit difficult, right? It's long, it's clunky, it's got a lot going on, okay? So what we developed was high-level languages, okay? High-level languages are what Java is, right? C is a high-level language, Python, there's lots of high-level languages that you can learn, all right? This is more understandable to the human eye, right? Area equals 5 times a representation of pi, right? So what happens is this line gets converted by the compiler into an assembly language format. That assembly language by the interpreter then gets further formatted into the ones and zeros for the computer to run. So we write this, the computer gets this, we run this, and we get our answers. Okay? All right. Sum some popular high-level languages. We're going to use Java, right? So one of the big benefits to Java is that it's what's portable, okay? It means that I can compile Java code on my computer, send you the resulting file. You can run it on your computer without having to have my source code, okay? Some other languages don't operate that way. C, for example, for if anybody has any experience with programming in C, you have to give somebody the source code for them to run your program. Okay, Java is not like that. Okay. Let me skip over a few more slides. Oh, I do want to make one comment about the operating system here. So you will have an operating systems course at some point within the next couple of years. And operating system is basically a special program that is the only program on the computer that is allowed to communicate directly with the hardware. So every other program on your computer, we're looking at PowerPoint. We have a Microsoft Teams meeting going on. If you were to look down into my Windows tray down here, you would see I also have a mail application open. I have Google Chrome open. Right? These are all examples of programs that have to go through the operating system if they want to do anything with the memory, with the hard drive, anything like that. They have to go through the operating system. The operating system is the protector, is the Guvenlik, right, for making sure that the programs that communicate with the hardware have the right to do so. Okay, so we all have to go through the operating system to get there. Okay. So why Java? One of the answers I gave was that it's portable. There's a bunch of other reasons here too. I won't go through all of those here today, but go ahead and if you're interested, take a look at these slides. Take a look at these slides when you have a chance. Okay. This is probably, nope, probably might be outdated. I don't know. If you have not already, make sure you download and install Java to your computer. You'll need a JDK, a Java Development Kit. I think a JRE is installed with the most recent JDK. Okay, and you are going to want to use a Java IDE. Okay, an integrated development environment. These are some popular ones here: NetBeans, Eclipse, IntelliJ, JGrasp. We went over those. Again, I will be using JGrasp for all the examples I do in class. It's the IDE that I'm most familiar with. By no means am I requiring you to use JGrasp. I think my professor at I was a teaching assistant for the Java class when I was in university, and the JGrasp was developed by the professor and his team that I was a teaching assistant for. So yeah, he would like it if you install JGrasp, but I'm not requiring it. Okay, but you will want to use. You're actually, as we'll see in just a second, you're actually not required to use an IDE at all. You can run Java programs. You can write and run Java programs without needing an IDE. Okay, so let's take a look at a simple example. Okay, so welcome, and we just want to print out to the line a message that says "Welcome to Java." Okay. You could actually write this program using Notepad. So you could create a text document, put a .java Java extension on it, all right, as the file name, and then you could run, right? You could compile and execute this without ever needing an IDE. Okay, maybe we'll look at an example of that here in just a minute. Okay, so we could run it using any type of text editor. Okay, again, this is something you can do, not necessarily something that I would suggest you should do. Okay, so what happens? We take this text, this .java, but it's just a text document, right? It's considered. We call that the source code, right? Then we compile the source code using a command line command. All right. We could have a compiler error. We'll talk about that in just a moment. But it creates this bytecode. And then when we run the bytecode, we get the result. Okay, so this creates this stuff, and then this we can run this on any computer. And I'll show you what happens when we compile it that makes it to where we can run it on any computer. Okay. All right, so when we run it, what we'll learn here today is when we go to run any program in Java, when we run a class, okay, this is called a class. This welcome is the name of the class, right? When we go to run the welcome program, it looks for this, what's called a signature. So it looks for a method that is public, static, void, main. We'll get into what all those words mean later this semester. Know this semester what void is and what main is, why that's important. Public and static will be a CSE 102 topic that we'll go into in depth. Okay, and then you'll also know what this is, right? So it looks for a public, static, void, main, something named main method that takes this as an argument, that takes this as a parameter. If it finds this, then what happens is it tries to run what's inside of it. Okay. And this is system.out.println is simply the way that we display stuff to the screen, and then it displays what's inside of there. Okay, so it tries to enter the main method, it sees this line, it runs this line, it displays that to the screen, and we're done. Okay. There's a couple of more examples there. Okay. Let's talk briefly about the anatomy of a Java program, the parts of a Java program. Hopefully before the first break, I haven't had a chance to look at the results of the form that I sent out. What I'm going to do is I'm going to take the results of that and use that for next week's class and going forward. Okay, I want to give everyone a chance. Actually, maybe what I should do is go over that form to make sure anyone who hasn't submitted it knows kind of what we're wanting from that. Okay, but I'm going to take the results of that and use that for next semester. But for today, we'll go ahead and have a break at 10:20 in 10 minutes. Okay? All right, so hold with me for 10 more minutes, and then we can take a break, all right? All right, so these are some of the parts of what's inside of a Java program. We'll get into this in depth here now. All right, so a Java program must have a class, okay? Now, the class name is welcome. All right. Now, one of the things that you're going to learn is the file name then has to be welcome.java, and capitalization is important. So there's a capital W, all the other letters are lowercase. That means the name of this file has to be welcome with a capital W .java. Okay. So anytime we name something, this public class, whatever, the file has to be whatever.java. Okay, so we have to have a class name. In order to run a program, we need to have a main method. Okay, it has to be specifically public, static, void, main, with a string, what's called a string array. We'll get into arrays in the second half of the semester. All right. And this has to be the arguments that it takes. Okay, so these are two things that we've now seen we have to have. Okay, in that format. Okay, now we have statements. We have instructions, or can't remember what the flowchart called it. I think it was instructions. All right, that was something to do, something for our program to do. Now, if we don't have this, when we go to run it, it's just not going to do anything, right? Okay. Now, some components of this statement. This statement terminator. So Java is a language that requires semicolons on the end of its statements. Okay. It has to end with that. This is how Java knows that this is the end of the statement. Okay. All right. Everything else, notice there's no semicolon on the end of this. There's no semicolon on the end of this. There's no semicolon on the end of this. This is a statement. It has to have a semicolon to end it. Okay. Some reserved words means that when the compiler sees these words, it knows there's something special it has to do. Okay. These words cannot be used as variable names. These words cannot be used as method names. Okay. So public is a reserved word. We can only use it for this purpose. If any of you have experience programming in Python, you know that in Python you're allowed to change reserved words. Java does not allow you to do that. Okay. I can't say public equals something else and make public something else all of a sudden. That's not how this works in Java. Public is going to have the same meaning the whole program long. Okay, and we cannot use it for other purposes. Okay, sometimes we want to have a section of code, so we'll use these curly braces to indicate the beginning and end of a block. Okay, so this open curly brace says this is the start. Everything after this is the start of the inside portion of the main method. Then I have my code, my lines of code that's part of the main method. Then I have this close curly brace that tells me that's the end of that block. That's the main method. So notice open curly brace to indicate the start of the class. The open curly brace to indicate the start of the main method. Close curly brace says that's the end of the main method. Close curly brace says that's the end of the class. Okay. All right. Some special symbols, open and closing curly braces is a block. Parentheses can be used for methods to indicate, to tell us the parameter list, the attributes, not attributes, the arguments that we're going to use. Okay. Brackets, these square brackets tells me that that's an array. Okay. These double precedes a comment line. Sometimes we want to explain what's going on with our code without actually writing code to do it. So this can be, so like the example up here, right? This program prints welcome to Java. That's not a line of code. That's a comment that tells me something about this code. All right. Where were we? Quotation marks is enclosing a string or a sequence of characters. And then again, the semicolon is the end of a statement. Okay. So we talked about this already. Yep. So this is how we say, okay, this is a method. Inside of this is the arguments, the parameters to the method. This tells me the semicolon, the end of a line. Right. These double slashes tells me this is a comment. The compiler will ignore this. The compiler will say everything up for this line, just ignore it. Don't do anything with it. Okay. This is about quotes. This is about what's inside of the quotes is a string. Okay. Make sure you use comments frequently when necessary. That you want to have a summary at the beginning of the program. What we're going to lab time is we're going to talk about Java.doc comments. Okay, Java.doc comments are stuff that we use to explain the purpose of a class or even a method, but something to tell us the information about what's coming, about the code that's coming. Okay. All right. Some naming conventions that I'd like to talk about. So you want to choose meaningful and descriptive names for stuff. Okay. The variable name A doesn't tell me anything the variable is for. A variable name like salary tells me something about what that variable is for. Okay. So you want meaningful and descriptive names. Class names will need to be capitalized the first letter. Right? So compute expression, for example, a capital C and a capital E. Right? Variable names need to start with a lowercase letter. There's some other things that we'll talk about. I think, actually, I don't have it in this set of slides. So I think it may be in this chapter 2, actually. So maybe we'll talk more about it there. This is a format right here. This is something called camel case. The reason why is because it's got big letters and small letters, and then big letters and small letters. And so it's camel head, like the camel hump, right? Okay. All right. Some other stuff. And by the way, everything I'm talking about, the appropriate comments, the naming conventions, proper indentation, block styles. All of these things are, the compiler doesn't care. You could actually write an entire program on one line of code as long as you have all of your curly braces, your semicolons, and all that. As long as you have all that correctly placed, you could put your entire program on one line of code, and the compiler would be just fine with that. Your reader, however, will not. You probably will have a hard time maintaining the code if you do it that way, right? And so the one thing you'll hear me say frequently is your code is going to be read a lot more than it is written. You will spend some time writing your code. You will spend some time making your code. But other people, class, for example, me and Taha Hoja, we are going to read your code, and we're going to try to understand your code in order to give you a good grade. Okay, if we can't understand it because variable names are not good, or indentation wasn't done properly, or block styling wasn't followed, it's going to be hard for us to understand your code. And outside of this class, when you get a job as a programmer, even worse, right? Because then you're going to be working on a team. Most of you will work on a team. There's very few lone programmers out there that just work by themselves. All right, and your teammates, the people you work with, need to be able to understand your code. Okay, so if you follow some type of convention, some type of coding style convention, that can greatly help. Okay, all right. And the final slide of this set, and then we'll take a break, is we're going to talk a little bit about some programming errors. So there's 3 types of programming errors. Syntax errors, sometimes called compiler errors, runtime errors, and logic errors. Now, syntax errors are examples of a syntax error would be a semicolon is not put where it needs to be. A closed quote is not put when an open quote was put, or a closed curly brace was not put when it needed to be. Okay, these are where the compiler cannot convert this code into executable code. It cannot understand it. Syntax is like grammar. Okay, so if I were to say something in Turkish with completely wrong grammar, so if I were to say, ben derse gidiyorsun, right? That doesn't make sense, right? I used ben on the front, but I said gidiyorsun. It's not right, right? That's a syntax error. Did I mean that I am going to class? Did I mean that you are going to class? Did I mean something else entirely? I don't know, because the syntax was wrong. The grammar was wrong, okay? So in that way, a syntax error, a compiler error, means that the code is not able to be compiled into executable code. Okay, these are the easiest to find. You have a syntax error, we'll see an example of this. The compiler tells you where the error is. Okay, runtime errors. Okay, compiler takes the code, compiles it into executable code, but it starts running, but it doesn't complete, because some error happens in the middle of the program, okay, to make the program stop executing too early, okay? So runtime errors would be like divide by 0. If we try to divide by 0, we can get a runtime error. Java will refer to these as exceptions, and in CSE 102 you'll talk more about exceptions and how to handle them. But runtime errors, the compiler compiles the code, I run the code, but before it's able to complete, before it's able to end properly, it ends abruptly. Okay, it's like all of a sudden, like it just stops. All right. Okay. A runtime error would be if this meeting were to suddenly end without me clicking anything. Okay. Okay, that's an error, by the way, not a good thing. All right. Logic errors are the final type of errors. Oh, by the way, runtime errors are second easiest to find because, again, the program will stop and we'll see exactly the line of code that the program stopped on. The reason why it's not as easy to find as syntax errors, runtime errors may be a result of problems earlier in the code. So even though it ended on this line, it may be that something earlier in the code caused the problem to be seen. You know, we'll see. I'll see an example of that. We'll see an example of that. All right. Okay. Final type of error that we'll talk about before we take our break, and I'm sorry I'm letting you out a little bit late on this break thing. Logic errors. Code compiles. Code starts executing. Code completes executing. But the result is not what we wanted. The result is wrong. That's a logic error. Okay. An example of this, if I went to the bank right now and I put my ATM card into the ATM and I said I want to deposit some money into my account. Okay, I need to pay a bill or something. I deposit 1,000 lira into my account, and then my bank says, great, and before I deposited the money I had 100 lira, and now I have 100 lira still. Wait, that's not right. I deposited 1,000. What happened to the 1,000? Oh, we don't know. It just went away. That would be an example of a logical error, right? I deposited the money, I ended the program, I got my card back, but my result was not what I wanted. My result was wrong. Logical errors are the hardest to find errors. Why? Because the program compiles and runs to completion. We have no clue where the problem happened. Okay. Nice thing about Java and a lot of Java IDEs is we have what's called a debugger that allows us to step through code to try to find those places, but we have to know what we're looking for. Okay, so those are the three types of programming errors. Hopefully, many of you have seen that on this slide there are 3 blanks, and we talked about that earlier in this class, what you're supposed to do when you see a blank. And so let's go ahead and some point before the end of this lecture, then you will need to do what you're supposed to do when you see blanks, and we'll do that. All right, but this will be probably the last time that I call your attention to a set of blanks on a slide. All right, so let's go ahead and take a break. Since I got you out of here about 5 minutes late, I'll give you 5 minutes extra. So what we'll do is we will start up part 2 of today's lecture at 10:35. Okay, see you in 10 minutes.